Hello. Today we are going to consider the calculation of trusses by the method of joints. We are going to do that by the example of a triangular roof truss. Let us make a sketch and a statement of the problem. The roof truss abuts upon brick walls. The support to the left is assumed to be a fixed joint, and the support to the right is movable. From the assumptions made for calculation of plane trusses, the joints are assumed to be hinged. The load on the truss exerted by the covering roof is transmitted through the beams abutting upon the joints of the truss, so the load is deemed to be concentrated forces. Let us define the forces in the members of the truss at a given load exerted by the roof. To start with, it is necessary to find for further calculations the angles alpha and beta. Tangents of the alpha and beta can be calculated from the geometry of the truss. The tangent of alpha is to be found from the triangle ADE, and the tangent of beta can be found from the triangle CEK. Then we find the bearing reactions, for which purpose we draw a free body diagram. The components of the joint reaction at the point A are directed vertically and horizontally. The reaction of the movable joint at the point B is directed vertically. The truss is in equilibrium under the action of an arbitrary coplanar force system. Let us introduce a reference system and write down the equilibrium equations. Only the horizontal component of the reaction at the point A is included in the equation of the projection onto the axis X. The vertical components of the reaction in the support and the concentrated forces F1 and F2 are included in the equation of the projections onto the axis Y. When writing down the moment equations with respect to the point A, we have to consider that the lines of actions of YA and XA pass through the point A, therefore their moments with respect to the point A are equal to 0. Let us calculate the moment of the force F2 with respect to the point A. To do that, we multiply the magnitude of the force by the arm, in other words, by the distance from the point A to the line of action of the force F2. The moment is negative because the force F2 is tending to turn the body around the point A clockwise. Similarly, we calculate the moments of the forces F1, F2, and YB. Solving the resulted system of equations, we determine the values of the reactions. Owing to the symmetry of the truss, the values of the vertical reactions YA and YB have turned out to be equal. Let us calculate the forces in the members of the truss. To do so, we number the bars. The joint A is the intersection for only two bars, the bar 3 and the bar 1. Therefore, we first leave out the joint A. Assuming the bars of the truss under tension, let us picture the forces in the members 1 and 3. Let us introduce a reference system for the resulted concurrent force system and write down an equilibrium equation. The projections of the force S3 are found with the use of the angle alpha determined previously. Solving the resulted system of equations, we find the values of the forces S3 and S1. The value of the force S3 has turned out to be negative, which means that the bar S3 is not under tension as we have previously assumed. The force in the bar S1 has turned out to be positive, which means that the bar is under tension. With the known force in the member 3, we now leave out the joint C. Then the forces in the bars 4 and 7 are unknown. The forces in the bars of the truss are illustrated as directed away from the joint, assuming the bar is under tension. The joint is in equilibrium under the action of the concurrent force system. Let us introduce a reference system and write down an equilibrium equation. When projecting the forces, we use the values of the angles alpha and beta determined earlier. To solve the resulted system of equations, we express S7 from the first equation and substitute it into the second equation. We then find the values of the forces S4 and S7. The values are negative, which means that both the bars 4 and the bar 7 are compressed. Let us now leave out the joint D. We then illustrate the forces in the truss members, assuming them under tension. Let us introduce a reference system and for the resulted concurrent force system, write down an equilibrium equation. When projecting the forces, we use the angle alpha. Having solved the resulted system of equations, we then find the values of the forces in the truss members. We see that S5 equals S4, and the value of S8 has turned out to be positive. It means that the bar 8 is under tension. From the symmetry of the truss and the symmetry of the load exerted on the truss, we conclude that the forces in the symmetrically disposed truss members are equal. Then we find the forces in the truss members 6, 2, and 9. When calculating the forces in the truss members, we have found that some of the members are under tension and some are compressed. A further calculation of the certain truss members depends on the kind of work it is to perform. The truss members to be under tension are calculated for strength, and the members to be compressed are calculated for rigidity.